Hello students, myself Antara Ghoshal from EC Department of Guru Nanak Institute of Technology, and this is my lecture series on solid state device. And today we will discuss about a topic under module 4, which is on field effect transistor. And and this is the subject name, that is solid state device. Code is EC301, and the total lectures for this subject are 36, and there are some course outcomes for this subject. First one is able to understand the energy band diagram, charge carrier transport phenomenon, and a recombination generation process of different types of semiconductor materials. Second course outcome is to able to understand the characteristics and current flow of semiconductor devices like BJT, JFET, MOSFET, and metal semiconductor junction and heterojunction devices. Third course outcome, which is able to analyze the design parameters of MOSFET, that is channel length and width, depletion width, surface field and potential, on resistance, transconductance, equivalent circuits, amplification factors, capacitance, noise margin, scaling and short channel effect of MOSFET. And the fourth course outcome is able to illustrate rectifying properties of different types of junction diode, importance of reverse current in solar cell and light emitting diode. Now, today we will discuss about the some parameter properties of MOSFET, and for that today's course outcome is third course outcome. Now under module 4, which is on field effect transistor, under this module there are different topics. Two main topics are junction field effect transistor and metal oxide field effect transistor. Under JFET there was construction, field control action characteristics, pinch of voltage derivation, and some numerical problems which I have already discussed in previous lectures. And after that, under metal oxide field effect transistor, there are different topics on this MOSFET. Today we will discuss about the MOS capacitance variation with gate to source voltage under low frequency and high frequency. First, for that we have to know what are the characteristics of capacitance voltage of MOSFET. Now, capacitance voltage characteristics. Already I have discussed about that. Already you know about that MOS capacitor is the heart of the MOSFET. Now, a number of informations about the MOS device and the oxide semiconductor interface, which can be obtained from these capacitance voltage characteristics, that is CV characteristics of the device. Now, the capacitance of the device is defined as C equal to dq by dV, where this dq is the magnitude of the differential change in charge on the plane on one plate as a function of the differential change in voltage, that is dV, across that capacitor. Now, what are the ideal current voltage characteristics of this MOS? Now, first, we will consider the ideal current characteristics of the MOS capacitor, and then we will discuss some of the derivations that occur from these idealized results. First, initially, we will assume that there is no voltage, that is there is a zero charge trapped in the oxide, and also that there is no charge trapped at the oxide semiconductor interface. Now there are three operating conditions of the MOS capacitor, that accumulation, depletion and inversion, which I have already discussed in previous lectures. Now this figure shows the energy band diagram of a MOS capacitor with a p-type of substrate. Here p-type of semiconductor is used, and for the case when a negative voltage is applied to the gate, including an accumulation layer of holes in the semiconductor at the oxide semiconductor interface. Now, if a small differential change in voltage across the MOS structure will cause a differential change in charge on the metal gate, and also in the whole accumulation charge, which is shown in this figure. That differential changes in charge density occur at the edges of this oxide as a parallel plate capacitor, and this capacitance, that is C prime per unit area of the MOS capacitor for this accumulation mode is just we can say that it is just the oxide capacitance, that is we can write that like C dash accumulation mode. At the accumulation mode, C dash equal to COX equal to epsilon OX by TOX. That is the capacitance per unit area of the MOS capacitor for this accumulation mode. Hence, we can say that it is oxide capacitance. Now, in next figure, that this figure A, that shows the energy band diagram of the MOS device when a small positive voltage is applied to the gate, including a Spitzer region in the semiconductor. And this figure B shows the charge distribution through the device for this condition. that is dq prime, and this is plus q positive charge which is applied, and here that is the xd, that is xd, and this is dx, and here the negative charge that is minus q prime, and this is dq prime. Now that shows the charge distribution through this device for this condition. Now the oxide capacitance and the capacitance of the depletion region are in series. A small differential change in the voltage across the capacitor will cause a differential change in the space charge width, and the corresponding differential changes in the charge densities, which is shown in this figure, and the total capacitance of this series combination for this depletion mode, that is 1 by C prime depletion equal to 1 by COX plus 1 by C prime ST. It is COX and CST, that is space charge density capacitor, and C prime depletion equal to, that is equal to COX C prime SD by COX plus CSD prime. Now, as we already know that COX equal to epsilon OX by TOX, and capacitance for CSD prime, that is equal to epsilon X by XD, epsilon X by XD, that is equal to, if we replace this equation by these two equations, then we can write C prime depletion equal to COX by 1 plus COX by C prime ST, that is equal to epsilon OX by TOX plus epsilon OX by epsilon S into XT, and from that C prime mean equal to epsilon OX by TOX plus epsilon OX by epsilon S into X dt. As the space charge width increases, then the total capacitance, that is C prime depletion, will decrease. Now, already I have defined the threshold inversion point, that at that condition when the maximum depletion width is reached. Now, but there is a essentially zero inversion change density charge, sorry, zero inversion charge density, then that this condition will give a minimum capacitance, that is C minimum. Hence, when a maximum depletion is width is reached, but that at that condition there is zero inversion charge density. For that condition, that will give a minimum capacitance, that is represented as C prime mean equal to epsilon OX by TOX plus epsilon OX by epsilon S into X dt. T for threshold condition. Now, next in this figure, that shows the energy band diagram of this MOS device for the inversion condition. Now, in this case, a small incremental change in the voltage across the MOS capacitor will cause a differential change in the inversion layer charge density. But the space charge width does not change. If the inversion charge can respond to the change in the capacitor voltage that is indicated in this figure, then the capacitance is again just the oxide capacitance. Means again that this figure that shows the energy band diagram of MOS device for the inversion condition, and when a small incremental change in the voltage across the MOS capacitor that cause the differential change in the inversion layer charge density, and the space charge also, but that space charge width that does not change, and for this inversion charge that respond to the change in the capacitor, and that is shown in this figure, that capacitor change in the capacitor voltage. Now then the capacitance uh, will be like same as the oxide capacitance, that is COX. That's why we can write that C prime inversion equal to COX equal to epsilon OX. Why? TOX. Means when the accumulation occurred, then also the capacitance of that accumulation mode, that was also C oxide capacitance, means epsilon OX by TOX. Next was depletion mode. For that depletion mode, the capacitance was changed, and after that, when the inversion condition come, then at the inversion condition, this is the capacitance that is same as oxide capacitance, that is COX equal to epsilon OX by TOX. Now in this figure that shows the ideal capacitance versus gate voltage. Capacitance versus gate voltage, that is C for capacitance and gate voltage is VG, or CV characteristics of MOS capacitor with P type of substrate. And that three dashed line, this that three dashed segments to the that three segments correspond to the three components, like COX oxide, COX oxide capacitance, CSD, and or C prime SD, and C prime main. Now the solid curve, that is the ideal net capacitance of the MOS capacitance, the MOS capacitor. Now Now at this moderate inversion, which is indicated here in this figure, that is the transition region between the point only when the space charge density changes with gate voltage, and when only the inversion charge density changes with the gate voltage. And this is the area for accumulation, that area is for depletion, and that portion for strong inversion. This is the moderate inversion condition. That portion for moderate inversion. Now the point on this curve that corresponds to the flat band condition, which I have already discussed in previous lecture, and the flat band condition occurs between the accumulation and the depletion conditions, and the capacitance of this flat band condition, which is given as C prime FB, equal to, that is flat band capacitance, equal to epsilon OX by TOX plus epsilon OX by epsilon S, root over KT by E into epsilon S by E N A. From this equation, we can see that the flat band capacitance is a function of oxide thickness as well as semiconductor doping. And this is the general location of this point on the CV plot, that is current and gate voltage plot. Now in this figure, that is the same type of ideal current voltage characteristics, that is C and VG, that capacitor and gate voltage characteristics, which is obtained for a MOS capacitor with an N type of substrate by changing the sign of the voltage axis, and the accumulation condition is obtained for a positive gate bias, and the inversion condition is obtained for a negative gate bias. This is the low ideal curve for the N type of substrate when N type of substrate is used. Now, this is the MOS capacitance variation with gate to source voltage under the low frequency and high frequency. For that, first we have to consider this energy band diagram when the MOS capacitor is considered for the inversion mode. In this figure, this figure shows, already I have discussed in previous slide, that is in this slide, that was the inversion mode. Sorry, um, that was the inversion mode. This figure shows the MOS capacitor with a P type of substrate and which is biased in the inversion condition. Now there are two sources of electrons that can change the charge density of the inversion layer. Now the first source is by the diffusion of minority carrier electrons from the P type of substrate across the space charge region, and this diffusion process is same as that of a that occurred in a reverse bias PN junction, which generate the ideal reverse saturation current. Now The second source of electron is that by thermal generation of electron and hole pairs within the space charge region. And also this process is again the same as the that in a reverse bias PN junction, which generate the reverse biased generation current, and both of these process generate electrons at a particular rate, and the electron concentration in the inversion layer that cannot change instantaneously. Okay, now if the AC voltage across the MOS capacitor changes rapidly, the change in the inversion layer change change in that inversion layer charge that will not be able to respond. Now the current voltage characteristics, then what will be the current voltage characteristics? Then the current voltage characteristics will be a function of the frequency of the AC signal, which is used to measure the capacitance. Now, if we consider for very high frequency, in that in the limit of very high frequency, the inversion layer change will not respond to a differential change in capacitor voltage. And this figure shows the charge distribution in the MOS capacitor with a P type of substrate. At a very high signal frequency, the differential change in the charge across the metal at the metal and in the space charge width in the semiconductor. This is shown in this figure at the metal and the space charge region of the semiconductor. The capacitance of the MOS capacitor then will be C prime mean, which I have discussed in a previous slides, that C mean equal to this. Capacitance of for this condition, the capacitance of the MOS capacitor will be C prime mean, and the high frequency and the low frequency limits of the current voltage characteristics, which is shown in this figure. And in general, high frequency corresponds to the value of a in order of 1 megahertz, uh, and low frequency, which corresponds to the value of the range of is 5 to 100 hertz. For high frequency, the value is order of 1 megahertz, and for low frequency, the value corresponds to the 5 to 100 hertz. That's all for today. That was the current voltage characteristics for high frequency and low frequency of a MOS capacitor with P type of substrate. And before that, that was the um, capacitance versus gate voltage of a MOS capacitor for N type of substrate, and that was for P type of substrate. Opposite of this, that is for P type and that is for N type. I think all these topics are clear to you, but if there is any question, then you can mail me. Okay, that's all for today.